All right. So this week we are going to talk about or continue our conversation about hardware from the lecture. And while the lecture was a lot of details about the current state of hardware, different forms of hardware, all of this, today's lab is going to be much more about how can we actually understand what we can do in the face of realistic hardware, no matter the system, whether you're talking about a photonic based quantum computer or NV centers or superconductors or whatever the heck else you want to use, topological quantum computers, one way or another, no matter how good the physical hardware is, there'll always be some noise. And so something that's really important to do in practice and something we can really dive into exploring with current technology is noise, and we can simulate that. So today we're going to explore noisy simulations, as well as a very particular thing known as the swap test. The swap test is going to be a little more advanced, so we're going to lightly go through that. We may not have time to go through it entirely, but we're going to really try to dive into noisy simulations and then run into this idea of the swap test. Some announcements before diving in. We have some exciting things coming up. First of all, we have a quantum lab tour at MIT on Sunday, this Sunday, February 25th at 10:45 to 11:50 a.m. Eastern time. So make sure to check that with your local time zone. The Zoom link and more info will be sent out soon. So no matter where you are in the world, you'll be able to see a live lab tour at MIT. This is a pretty amazing experience and definitely something that's pretty invaluable to be able to do outside of learning these topics, to really see them in action in a lab. So I really recommend you go there. Know that more info will be sent out soon. Recommend you to keep an eye on your email and on the Canvas announcements page. Later on, we'll have a few more weeks of classes, and then we're going to have spring break from March 10th to the 16th. This is a good set of dates to write down. We will have no classes, no lecture, no labs during this week from March 10th to the 16th. It's a little spring break, whether it's lining up with your school's spring break at all or not. It's just a nice chance to get a little breather, and then we'll come back with a few more topics and projects after that. Okay, know that there is a code provided, the attendance code provided at the end of every week. I know last week was a little funky, so I'll just say now that the lab code from last week was 9801. 9801 was the attendance code for lab 16. That is not this week's, that is last week's, in case you didn't get it. But for this week, we will announce it at the end of today's lab. So watch to the end of the recording or stay on till the end. I'll make sure you get it before time is up. So today we're going to dive into running on real devices today, what that involves a little bit, and then we're actually going to talk about how to implement noisy simulations of quantum computers. And lastly, we'll wrap up with a sort of specialized topic, the swap test. Some key goals today are for you to recognize how to run simulations in Circ with noise throughout a circuit and at specific moments of a circuit. So really it's about taking what we already know about simulating circuits in Circ. This is something we've done many times. It's really what you've been doing all throughout since you started with Circ. But now we want to be able to add noise to that so we can really see what would this look like in practice, in reality, so that our simulations can be that much more realistic. We will also want to be able to recognize how to use the swap test to measure something known as fidelity, as well as how to use it to characterize noise in a circuit. These last two ideas are kind of secondary. The first one's the most important by far. The second two, the last two, are really special topics. You can tell there's a lot of new words there, new terms. They're just kind of a little bit of exposure, let's say. So let's go ahead and get started. First, we're going to talk about running on real devices today. This is more of a discussion. We're not going to do anything in practice. So running it in real circuits today adds several complications to what we've seen so far. This includes the actual running on real devices, which is to say that there'll always be some noise when we're doing this. Always, there'll be some noise. And unless you have your own quantum computer, you're sharing access with others. What that means in practice is if you and I and everybody in this lab wants to go ahead and run a circuit on a real quantum device, assuming none of us have our own quantum computers, we're going to have to be sharing that quantum computer. So that means I'm going to have to wait for your circuit to run, and you're going to have to wait for someone else's circuit to run. And what ends up happening is there's often a long line or queue to use these devices. Now, you can get special access at times. Researchers, for instance, often get special access to devices so that you have plenty of time to do this. But nonetheless, generally, the more people that we have using these quantum devices, the more you're just going to have to wait your turn to use them, which can really add on time. I'm talking hours, days, even weeks at times to get your results back. So this is obviously much different than simulating these circuits and seconds later getting the results. There's also, so these are issues we'll have always, really, long term. I mean, maybe long-term quantum computers will be cheap enough that we could all have our own, but that's probably a little ways off, a long ways off. We'll talk more about kind of the expected timelines of that down the road. But realistically, we'll probably always be sharing access to quantum devices. So that's something long-term. But today, really, we have to realize that we're dealing with not just some noise, but a lot of noise. Noise is always going to be present, but today's devices are really, really noisy. We're in what's called the NISQ era, the noisy intermediate scale quantum device. Noise is just part of the deal, and it's not just a little thing either. It is a lot of what we're dealing with, meaning that when you try to run a circuit, what you get is often not really what you wanted to do. Also, the available devices are small. That's the intermediate, the I part, the intermediate scale part of NISQ. The devices are not that big. So if you want to run Grover's algorithm for some massive database and where each possible solution that you're looking at is encoded in thousands or tens of thousands or millions of qubits, as the case may be, well, that's just not going to happen. We just don't have those devices yet. And there's often many others in line ahead of you to use devices. So while long-term, hopefully, even if you're using cloud access quantum computers, say, hopefully that'll not be too long and it'll be pretty easy to use. But right now, oftentimes, there aren't that many devices out there. We're struggling for access. So it can take a little while to run on these devices. And accessing those devices can sometimes be a complicated process. It's often very different whether you're doing it in Cirq or Qiskit or QSharp or wherever. Which devices you have access to are complicated. So running on real devices today is completely possible, but there's a lot of complications there. Now, in particular, if we want to do this with Google, which we won't be doing today, so that we focus on a few other things that are a little more general, let's say, we do want to make sure that you know there are some resources to use with Google. They're also linked in the summary of key concepts sheet for this week. So I highly encourage you to take a look and poke around there yourself. But Google provides a number of resources to help you begin this process, largely including, on one hand, what they call the quantum virtual machine. And this is a virtual version of their real quantum chips. So Google has real quantum chips. They've done some quite impressive things with them. And you can access a virtual version of this so that you can really understand how things would work on them. You can also interface with other providers through Google, through Cirq. For instance, all of the companies shown here, you can get access to their chips or to the chips that they have access to. Basically, you can get access to a lot of different quantum computers within Cirq, within Google Colab, within the whole Google ecosystem. You can actually get access to a lot of different providers, which is very nice. So you can run the same circuit on many different devices if you wanted. Now, all of these options and the others from other providers, for instance, if you went through IBM and Qiskit or Microsoft directly or something like that, are often very, very specific. So how you access each individual device is going to be really specific. And we've decided that it's just not really worth it today to learn one specific way to do that. Rather, we want to talk about a more universal task, which is really crucial and one of the huge things that people are doing today, that researchers are doing today, which is really on understanding noise. Because the only way we can overcome this noise and learn how to deal with it is to understand it. And in fact, over the next couple of weeks, we'll be seeing some things we can do with and to the noise. Today, we just want to understand what it is and how it can affect our circuit. So that brings us to noisy simulations. Noisy simulations, what are they? Why are we doing this? So since running on hardware can take a long time, or it may not even be possible in some cases, it's really important for us to be able to understand how different types of noise affects our computers and what we can do about each type. This is arguably one of the biggest questions that we are facing today is, what can we actually do with our noisy devices? How does noise affect things? And not just generally as a concept, but specific kinds of noise at specific points in our circuits, things like that. So for this reason, simulating noise is crucial for the advancement of quantum computing. If we want to get computers, quantum computers, where noise is not an issue anymore, well, we need to understand the noise we're facing in order to deal with it. The way we do this generally is we need to be able to somehow provide some really concrete description of the specific noise that we may be dealing with. We call this description a noise model, and this can come in many different forms. So a noise model is really just a very general term, and it can mean a lot of things. It can look a lot of ways. You can encode it in different ways, but it can come in many different forms. For instance, you have something where the 0 and 1 states are flipped. For example, the 0 state goes to the 1 state, or some complicated superposition has the 0 and 1 state flipped. So notice here, we have a smaller coefficient in front of the 0 state and a larger in front of the 1 state. But then after this error, or this noise, we get a resulting error that says, well, now actually 0 is more likely than 1. So what this error, this type of noise does, is it comes in and it infects our qubit in such a way that our 0 and 1 states flip with each other. We call that a bit flip. The idea is you're just flipping the bit from 0 to 1 or 1 to 0. So very importantly, it's either way. 0 and 1 just get flipped with each other. We can also have a phase flip, which is where the sign between 0 and 1 is flipped. And I see there's a little funny guy there that got thrown off. But for instance, when you have a 0 state, a phase flip error actually doesn't affect you. It's okay because there is no sign between 0 and 1 that we're worried about here. 0 just goes to 0. So in fact, with a phase flip error, we get no issues here. On the other hand, we start to get an issue with superpositions where we have a sign between 0 and 1, it gets flipped. So where here, the likelihood of measuring 0 and 1 is the same before and after, unlike with the bit flip, the phase flip changes this from a plus to a minus. For instance, it would change the plus state to the minus state. There's other kinds of errors too, where you're not just flipping things necessarily, and a very classic example is amplitude damping, whereas all states collapse to 0. Every state just goes to 0. For example, if you start with the 0 state, okay, you're fine because that just stays 0. But if you have some complicated superposition that's really important, that you have this very specific one, doesn't matter, amplitude damping comes in and says, gone, I'm getting rid of all the other amplitudes, I'm damping them, that's the idea, and you just end up with 0. You can see this is a very destructive type of noise, right? You have all this kind of quantum information, you have this nice, beautiful quantum state that's this unequal superposition, and then suddenly you just get 0 out. Amplitude damping is a very nasty type of noise. Now, in general, we could think of a single qubit noise as what's called depolarization, which is that at random, you just move around the block sphere. So that's an X, Z, or a Y gate. Now we haven't seen the Y gate or explored it really, because that gets into some math we're not so concerned about, and you can do pretty much everything with X and Z gate that we'd want. But the general idea is you randomly just get rotated around the block sphere, and you don't even know necessarily which of these was applied. It could have been that you were applied an X gate or a Z gate, or maybe this Y gate. So for instance, if you had the 0 state, at random, you might get a 1, or you might get this mysterious looking state, which in its essence is just an equal superposition. If you had some superposition like we've been seeing, you have 3 possible states that come out, where maybe the 0 and 1 state flipped because you applied an X at random, or maybe the sign flipped because you applied a Z at random, or maybe you got something even more complicated in there with this Y gate. But the point is that not only if this noise is applied, do you get some outcome that's not necessarily the same as what you started with. So you fundamentally changed your state. That's bad. You had a state you wanted, noise came in and said, nope, I'm changing it. But you don't even know what the outcome is. You don't know which of these 3 comes out. So you can imagine that's really bad. At least with amplitude damping, you know, okay, this happened, I have a 0. The main idea of depolarization is that it introduces uncertainty about which state we're in more than other forms of noise. So that's kind of summarizing this idea that I've been talking about. So the point of this is not for you to memorize these specific kinds of noise, but rather just to learn that there are different types. And now let's see how we can actually implement these ourselves. So we can create a general noise model in Circ with this line of code. First of all, it's an object. The noise model is an object. So you store it in a variable, call it whatever you want, call it Bob, call it Alice, call it noise. As usual, we do our circ dot and then whatever we're looking for. So we have our noise name. We'll see examples of this in a moment. And then the probability that that noise gets applied. For instance, we could say, I want a bit flip error with a 5% chance. So this is the probability or the fraction. With a 5% chance, I flip the bits. That's this noise. We store that in there. We could also do a phase flip with, say, 0.9. That's a 90% chance. That's really, really likely. There's a 90% chance that we flip the phase of our qubit state. Or we could do amplitude damping. In this case, we do it with 100% probability. So that just is going to apply amplitude damping. 100% chance it's amplitude damping time. And you could do something like depolarization. You can even say, hey, there's a 0% chance. Now, there's really no point in doing this, but just to give you an example, technically, these are the full ranges of numbers you could use. A 0% chance of applying depolarization. Okay. And as usual, I want to emphasize, you really don't need to memorize these. We have them in the cheat sheet. You can look them up, but it's more just knowing how this works generally, that you do circ dot, the name of the noise model you're looking for, and then you tell it the probability of that noise happening. So we're going to focus on 2 main ways to add noise to circuits, although I will emphasize there's actually a number of ways to do this. So we're really just picking and choosing a couple that are particularly helpful. First of all, we could have one where noise can happen at any time and any number of times in our circuit, right? This is in some sense the most general and the nastiest of the noise models. Is we make our noise model, and then we say, I'm just going to run my circuit with this noise. So we create a version of the circuit with that noise in it. We can then simulate that if we want. So we can have our circuit and then we can simulate it. So you can create a version of the circuit with and without the noise, for instance. You can also just go ahead and run this circuit. It's a fully normal circuit. Circ knows what to do with it. So you do sim.run like we normally do, and then you run your circuit. Or you can say, you know what, I'm just going to say there's a very specific point in my circuit that this happens. and it's going to happen to very specific qubits. So in this case, if you had a 5-qubit circuit and bit flip errors, every single qubit could have a bit flip error at multiple points throughout wherever. In this case on the right, we're saying, actually, just like I can append a gate or a measurement, I'm going to append noise, and I'm going to say on which qubits that can happen. This just allows a little more control for you over how you do this, and it really just gets buried into your circuit at a specific point to a specific qubit. What I want to emphasize here is this really is structured the same as appending a gate or a measurement or anything else that we've seen. Whereas on the left, this is an entirely new thing. We're saying we have a version of the circuit with noise throughout. So let's go ahead and actually practice this together. And I think this is where we can really start to see things come together. So as usual, make sure you make a copy of the notebook. And let's go ahead and run this cell up top to make sure got everything we need to get started. Oh, just a little mistake there, just get rid of that. Okay, and while that's all loading, remember to always do this first. And if you have errors later on that seem strange, always remember to go back up and check you did this. Now let's go in and let's work on part 1.1 and specifically problem 1 together, and then you can all continue with the next couple. So first of all, in this, we're just looking at adding general noise. So here we're just talking about, I just want noise throughout my circuit. I don't want to get so specific as when or to which qubits it's applied. We're just going to add general noise. So first, let's run this cell here to just create a circuit that we're going to be wanting to run ideally, and then we're going to introduce noise to. So this is all code that if you take some time to look over should be actually pretty recognizable, should be stuff you could do yourself. This is something we've done before. This is actually creating the bell state and then measuring at the end. So we're just doing this just to get this out of the way so you don't have to worry about it, but technically you could do this yourself. Now, in this problem, we want to simulate this circuit above. We want to create the bell state, but we want a 5% chance of depolarizing noise just anywhere in the circuit. So let me zoom in a bit so we can get a nice view. We can see here that we already have the general flow laid out for us. First, we need to define our noise model. Then we need to create our simulator and simulate the circuit with this noise. And then we can look at the results. That's all provided for us. So there's really two things we need to specify here: the specific noise model we want to use, and how we want to define it, and then how we want to use it in our simulator. So let's start up here. We want a 5% chance of depolarizing noise. So we already have circ.depolarize here written for us, but we need to specify, well, with what probability? We want 0.05. This is the fraction, so it goes from 0 to 1. So a 5% chance is 0.05. It's not 5, not like that, or like this, or anything else. It's 0.05 for a 5% chance. This defines the noise model. But so far, this is just a noise model. We've just defined this object. It's not doing anything. We need to actually specify, hey, I want you to use this when simulating. We want to simulate a version of the circuit with this noise. So here, all we do is we just say what the noise is. And then everything else is provided, so we can go ahead and just run this cell, and out we get something like this. We get the 1, 1 state. And if we run this again, we might get different results. Now, right now, we're just running it once. That's the default. So we're only seeing one result at a time. But of course, we've seen that we can add this parameter to get a lot of results all at once and just make sure that we get nice results. 1,000 is probably a little more than we need, but just want to really show the results here. And here we go. So what I've done is I've specified the noise model, depolarized with a 5% chance, and then I've said I want to run my simulation with this circuit, but I want it with this noise, and I want to repeat that 1,000 times. You can probably do it 100, and that's totally fine. But now I want to look at this together before we go off. We are preparing the Bell state, the kind of plain old vanilla Bell state. So we should expect 0, 0, or 1, 1. Right? We've tried to create entanglement with this H and C naught. We've tried to create this entanglement so that they always agree with each other, 0, 0, and 1, 1. But somewhere along the way, this depolarization noise can happen with a 5% chance on any of the qubits. And so what ends up happening is sometimes you get this result where actually you don't get the one you want. Something happens and you actually lose that entanglement. Now, because it's only 5% depolarization, this doesn't happen too often, so maybe we're okay. You notice most of the time we get the 0, 0 state or the 1, 1 state, which is what we want from the Bell state. But now with this depolarization, there's a small chance, it's not exactly 5% because of the fact that it can apply to multiple qubits multiple times, things like that. And sometimes actually the error with depolarization won't have an effect, but sometimes you get the wrong state, the state you don't want. Now that's actually really important, not just because, okay, I tried to make a state and I didn't get it, but here you can imagine we want some entanglement for some reason. That's usually really important. Entanglement's a huge part of quantum computing, a huge part of the power of it. And just with even 5% depolarization, there's a chance that we don't get it when we want to. There's a chance that we create a state and we think it's entangled, but this depolarization noise came in and suddenly we didn't get entanglement. Our entanglement was lost or it was at least lessened, and that is not great. Okay. Before moving on, I want to see, because I've gone through a lot of stuff so far, are there any questions on this so far? Questions on the coding or the results here of what we're looking at here? All right. If not, go ahead and work on 1.1.2 and 0.3 on your own. So basically wrap up part 1.1 on your own. I'm more than glad, I'll be right here, I'm more than glad to answer questions, but generally go ahead and work on these two problems. I'll give you a couple minutes to go ahead and do that. Give it one more minute to wrap this up. Go ahead and let me know either directly or to the whole group when you're wrapped up, when you're done. We'll come back together in 1 minute. All right. So let's go through this together. So in problem 1.1.2, it is very similar, but now we want the same circuit with a 25% chance of depolarizing noise. So we're going from 5% to 25%. First of all, we need to define our noise model such that it's depolarizing noise that's already given to us with a 25% chance. That's 0.25. Again, it's not 25, 0.25. Then we need to run this circuit, but with the noise like we had up above and with our specific noise model defined here. And then just for good measure, we're gonna rerun this, let's say 100 times. Let's go ahead and give that a try. Here we can see that we have a similar effect, but much stronger, right? Our noise is 5 times more likely to happen. We went from 5% to 25%. 1 out of every 4 moments, let's say, there's a chance that we get depolarizing noise. And so now what you end up getting is there's arguably still more times that we get our nice entangled state where we're 0, 0, 1, 1. But notice that there's a lot more of our other states mixed in here. And you can see things just get a lot more muddled. For instance, when I look at this, I go, okay, I'm pretty sure this is meant to be the Bell state. I'm pretty sure that's what I'm actually preparing most of the time, but sometimes it gets like hurt, let's say. Here, it's a lot harder to tell. I mean, this could just be a spike, and if I do this 1,000 times, maybe I'll just be that much more confident in the results. But generally, still, no matter how many times I see this, how many times I run it, there's always just a lot of these going on in here, these middle ones that are not supposed to be the outcomes. We're not supposed to be able to measure the state 1, 0 or 0, 1 from this Bell state. These are incorrect. These are errors that have cropped up because of this depolarization. Okay, so let's take this even further and do a 100% chance. Now, something that I've done before, and I always want to emphasize is, while doing it very carefully, you could just copy and paste. Notice most of this is the same. Really, the only thing I need to change is the chance of the noise, right? Or if I change the type of noise, changing it there too. So 100% is 1.0. I should also change the title down here, but I'm less concerned about that. And otherwise, we can just run the same thing. Again, notice at 1,000 repetitions, it takes a little bit to load, but it's not too much. Notice here, it's a complete mess. For some reason, the 1, 0 state is a little more likely, but realistically, all of them are about as likely. In fact, the 1, 1 state's the least likely, even though that should be one of the only 2 states present. This is just an absolute mess. This is just complete randomness. We're just randomly guessing bits. At this point, the noise has completely destroyed our state. So that's what happens when you have a 100% chance of depolarizing noise. It is guaranteed you'll have this noise. How many times is not necessarily guaranteed, but it's guaranteed you will have it. And you can see that just destroys things. Now, this is actually realistically what we'd see. And a lot of what people do with these simulations is they say, okay, I have the real results of running on a quantum computer. Now let me find the exact simulation, the exact noise model that creates the same results. And that's going to be my explanation of what's happening, of what noises actually we're dealing with. Now, sometimes you may be aware that it's not so realistic that the noise is going to be the same throughout at every point. Maybe you have some qubits that are noisier than others. Maybe you have moments in your circuit that are less noisy or more noisy. So it's very valuable to append noise to a specific moment. So what we're going to go ahead and do is just continue on with part 1.2. Before I do that, I want to see, are there any questions about these parts so far, about what we've done so far? Okay. So similarly, let's go through one together, and then I'll let you go off and do a couple on your own. Here, we're going to see how to simulate noise by appending it to a specific moment in a circuit. That means the rest of the circuit is completely noise-free. It's ideal. It's exactly how we've been running it all year. This gives us a little more granular, precise control, but we also have to be careful because sometimes leaving parts of our circuit completely noise-free is just not realistic. So unless we get really intense about adding all sorts of different points of noise in, it actually can be less realistic sometimes. On the other hand, maybe we can just create a situation where there's like one moment in our circuit that's really exposed, and then the rest are not so much. So let's go ahead and simulate this circuit with a 100% chance of depolarizing noise on just the 0th qubit before applying the H-gate. So notice there's a lot more specifications here. But let's start with this one part at a time. First of all, we want a circuit with a 100% chance of depolarizing noise. So first we want to define our noise model. Our noise model is circ dot depol, and we can look up here to see depolarize. And we want a 100% chance. That's our noise model. We've just defined what it is. Now we can do whatever we want with it. Well, specifically, we want it just applied to Q0, and we want it before applying the H-gate. So we look in here, we already have it set up for us. It's the same circuit as above. We're preparing the bell state. But what we're saying is at the very beginning, right before that H-gate, we want to append noise, this noise, and we actually just want it on the 0th qubit, like this. Just like we can say I want then an H-gate applied on just qubit 0, we can say I want this noise applied on just this qubit. So we can do this, we can run, that's all we need to do, define the noise model, add the noise right beforehand. And notice now when we look at the circuit, we have our normal circuit here, but we also have this part here. What this is D for depolarizing and 1 for 100% chance. It's just telling you, hey, you have a chance of noise here. It's in fact 100% chance. Then the code here is provided already. We can just run it in order to simulate this and get the result. Now, in this case, we actually are fine. Even though we have a 100% chance of noise, as in it's guaranteed you get noise there, it's actually not an issue. This is interesting. This is subtle, but it's interesting because this shows that even though when we had a 100% chance of depolarizing noise just anywhere in the circuit, it completely destroyed things, having the exact same noise, guaranteed depolarization at the very beginning on just Q0 actually doesn't matter. Why this is comes down to the fact that we then we have the 0 state. We guarantee we apply some sort of mistake to it, some sort of noise to it. But whatever that is, we then apply the H-gate, and it doesn't really matter because we just go into an equal superposition. And then we go ahead and create the bell state. So really, this actually isn't so bad. What I want you to do now is look at several other cases of doing this, which is the exact same noise applied on the exact same qubit, but at different points in the circuit. So I want you to go ahead and do that now. I'll give you a couple minutes to do it. And let me know when you're done or if you have any questions. But do exactly this. I'll leave this code up as well. Go ahead and do exactly this, but now just at different points throughout the circuit. And again, I really highly encourage you to do a lot of copy and pasting as needed, but just being very careful about where in the circuit you're applying things and what needs to change or stay the same. Be another moment or so. Okay. So in this problem that we did together, we wanted to simulate the circuit with a 100% chance of depolarizing noise on just Q0 before applying the H gate. I know that's a lot, but again, you break it down part by part. And now look, it's the exact same thing, 100% chance of depolarizing noise on just Q0, but now we want it after applying the H gate and before applying the C naught. So all that's changed is just the exact moment in the circuit we do it. So what I'm going to do is I'm just going to copy and paste my result in. But very importantly, I'm going to take the noise that I applied in the beginning, and now I'm going to put it between the H gate and the C naught as requested here. Everything else is the same. We can run this and see, hey, look, now it's sandwiched between. It's a good way to double check that you got it right. Circuit should look like this. And then we can go ahead and just run that. Okay. So now it seems like it's okay still. Seems like it's okay. And again, that's because, okay, we have this 0 qubit. It's in the plus state, or it's in the plus state guaranteed because we apply H. And then you get depolarizing noise. But all that depolarizing noise does is it flips things around. Unlike amplitude damping, which could be very dangerous here, this just flips things around. It could be flipping 0 and 1. It could be flipping the phase. It doesn't really matter because we have an equal superposition. So we can still get that nice entanglement out. So you see, okay, that's yet another case where even if we're guaranteed to get noise, this specific noise at this specific moment doesn't matter. And then we can do the exact same thing down here, where now we want it after the C naught gate, but before measurement. So we're really just moving this on down. Okay, define that, make sure that your circuit matches up with this. And then now let's simulate it. Now we have issues. So we were seeing good so far, right? It was totally fine if we had a 100% chance of noise before we started, in the middle of it. But if we do it after we've created the Bell state, then we get an issue. In fact, we're wrong most of the time. And notice we ran this 1,000 times, so we can be pretty confident here. I mean, you could run it even more if you wanted, but this is not good. And what's happening is we're creating the Bell state in total here. And then once you have the Bell state, you have this entanglement. That's now pretty fragile. And then you apply this noise that can start changing all sorts of things up. It can flip your bit, it can add a phase, it can do all this. And specifically, I will say, entanglement that you've created here. Entanglement is all about sort of blurring the lines between individual qubits, saying qubits 0 and 1 are entangled. The difference between them, even in a quantum sense, is not as clear as it was. But then we apply noise to one specifically, and that suddenly sets it apart a little more. So more conceptually, more generally, more physically, what's happening here is we create entanglement, and then noise comes in and says, I'm actually going to pick out one of the qubits. And that kind of sets it apart, and it just destroys things. That's kind of hand wavy. It's a little general, but that's the general idea of what's happening here. Entanglement's pretty fragile. There's now some forms of noise wouldn't be an issue here, but this one is. So you can see this is a different kind of question than what we were asking above, which is what happens when we just have noise throughout our circuit anywhere, anytime, to any qubit. Then here, where we're saying, no, I'm going to add it to each specific moment, this, I would argue, is a really good way to understand noise, to just place it in different points, increase or decrease the probability, change the type of noise, just move it around and just get a feel for it. Understand what role it's playing. Why would it not cause an issue here? Why does it cause such an issue here? Okay. So with that, I want to stop and see if there's any questions on this. I know this is a lot of information we've taken in, but I just want to see our general questions right now on this. All right. Then I would also love to take a poll quickly, just see how you're doing. All right, the poll is out. Go ahead and just let me know how you feeling. Again, this is anonymous. I just want to know how you're feeling. Is this really, really overwhelming? Too much? You're lost? Very confused? Do you need just a little more practice? Or are you feeling great? You're good to go. Can keep moving. Okay, I'm gonna got most of the responses, just one or two left. I'm gonna close in 5, 4, 3, 2, 1, and 0. There's always someone that gets in at the last moment. I feel like it's almost a game. Really good at it. All right. All right. Seems like people are doing pretty well overall. I'm seeing a lot of 4s, a couple 5s, a few below that. That's fine if you are. All right. Let's keep moving. Now, I also will say, I know we're close to the end of our time here. So I am just going to go ahead and before we go up to this last part, I'm going to go ahead and share the attendance code. The attendance code is 1016. So attendance code is 1016. Just in case we get to the end time and you need to get moving, we're probably going to go over a little bit. So if you have to get going on the hour, that is completely fine. You're free to go. You have the attendance code. But if you can, I encourage you to stay and listen to this discussion and see how to implement this swap test. So we've now seen how to simulate noise. Now let's talk about, well, what do we do once we have some of this information and once we have more quantum computers? We really, with all of this information, we need some way to actually know which ones to use. We need to know which quantum computers to use, which ones are best for certain tasks, all of this. And this will, in fact, also help motivate what the next generation could look like. If we know what computers we have now that are really good and which ones are not so good, well, then that can say, well, okay, why don't we make more like that other one, right? Or, hey, this one on the left is really good for one purpose, and on the right, it's really good for a different one. So why don't we specialize those or something like this or combine them? So we need some way to compare how real quantum computers work. One way we can do this is to understand how they work in comparison to the ideal simulated version. And there's a couple ways we can do this. We can say, okay, let's look at what's called the topology. That's one way to put it. It's the build of it in some sense, which is how many qubits are there? Are you comparing an 1,000 qubit computer to a 2 qubit computer? Those are obviously going to be able to do different things. How are the qubits connected? If you have 5 qubits that are all connected to each other, as in you can apply an X gate between any of them, or sorry, a C naught gate between any of them. You can do whatever you want, connect all of them, have them all entangled, versus an 100 qubit computer where none of them are connected. You can't do a C naught gate. There's no way to create entanglement, for instance. I don't know. Those are going to do different things, right? There's also ways to understand, well, how many errors do we face on each device? And this is generally known as error benchmarking. So what this means, what error benchmarking is saying, okay, how much noise does the computer face when we run a certain gate or a circuit? For instance, when I run the H gate, is that really, really full of errors? Or is that okay? Can I rely on that? And what type of noise does the computer face? For instance, is it all bit flips? Is it all depolarizing? Is it all of the possible errors? Is it specific ones? Are there specific points? There's a lot of questions that you can really dig into and ask. And all of that is known as error benchmarking. For instance, are there also certain qubits or connections that are noisier? This is a very real thing. In our simulations, we don't usually have this, but in reality, these qubits are physical things, and the connections between them allowing you to apply something like C naught gate are physical things. They're wires and they're other materials, they're lasers. That means that there can be problems with some more than others, right? There can be some qubits that are very, very noisy, not great, and other ones that are really, really good. So we're going to focus on this aspect today. Specifically, we can benchmark by comparing quantum states that we've prepared. So one way to see the effect of noise is to compare the quantum states that are output with and without the noise. As in, I have a circuit and I want to prepare a state. How does this compare when I don't have any noise? I have the ideal system and I get out exactly the state I want, versus when I do have the noise. We can do this using a very important quantity in quantum computing known as the fidelity. The fidelity measures how close or similar two quantum states are to each other. That's the general idea. Fidelity is how close they are to each other, how similar they are to each other. Technically, it's measured as this. It's the inner product of them squared. It's the amount of overlap squared between them. So for instance, the fidelity between two states that are completely opposite, 0 and 1, for instance, is 0. The fidelity of, say, the plus state and 0 is 1/2. They're 50% similar in some sense. Or a state with itself has a fidelity of 1. So fidelity can range from 0 all the way up to 1. 0 at its lowest. If it has a 0 fidelity, those states could not be more different. If it has the fidelity of 1, they are the same state. We can use the fidelity to see how close the noisy version of the state is to the intended perfect state. In other words, we can look at this fidelity of the perfect state with the noisy state, where we go from 0 being the largest possible error, as in we wanted this perfect state, but our noisy state was as far away as possible, to 1 being there's no error at all. Our quote unquote noisy state is actually what we wanted, the perfect state, so we're okay. But how do we actually measure this, right? This is kind of this mathematical, theoretical concept, and maybe your head's spinning a little bit from that. How do we actually measure this? We can do this using something known as the swap test. This is a very famous circuit in quantum computing, and the general setup is this. You have two states. We're going to start with just single qubit states, or we're only going to work with single qubit states. And then you have this extra qubit. We're going to call it an ancilla qubit, ancilla. You don't need to worry about that vocab necessarily. That just means extra. It's a bonus qubit. It's an extra one that's kind of like a scratch pad that just allows us to write down our results. So what we do is we have our two states. Let's say the state we want and the state that we have, the ideal state and the noisy state. We then want to apply whatever this swap test circuit is. We're going to see the details in a moment. Whatever the circuit is, we want to be able to apply it. And then what we're going to do is we want to be able to measure the fidelity out of this. Specifically, we're going to indirectly measure it from the ancilla bit. So we're going to use the ancilla bit to sort of record some information about the fidelity and then get this out. This is the general setup we're looking for, and the swap test circuit is what allows us to do this. Let's break this down into 4 steps. First of all, we have our ancilla bit and our 2 states. What we do is, and written in cats like this, what we do is we first apply an H gate on the ancilla. We put it in a superposition, equal superposition. That means we go from this state up here to this state down here. It may look very complicated, but what we've done is we've applied an H here. Notice this is the ancilla, this is state 0, state 1. We apply this, so this is a plus state. Well, if I expand that out, I get this somewhat complicated state looking here, but notice we always have state 0, state 1, state 0, state 1, but we have an equal superposition of 0 or 1 for our ancilla bit. This is just a fancy way of applying an H gate to the ancilla. Then we apply what's known as a swap gate that's controlled by the ancilla. It's a controlled swap gate. This is a more complicated gate. You don't have to worry too much about it. We're going to see implementing it is actually really, really easy. But what it does is, unlike a controlled NOT that takes that when the control bit is 1, it flips the qubit. What it does is it swaps 2 qubits with each other, 2 states with each other when the ancilla or when the control is 1. So if we go through this, we can apply the controlled swap on the left here, and it says, well, the control is 0, so we don't do anything. But here the control is 1, so now we've swapped these. So notice that the order is flipped. Now we have state 1, state 0 here. We've flipped the states of the qubits. That is the definition of the controlled swap gate. That's how it works. And because we have this superposition, we get both possibilities happening at the same time. This is a new gate for us. Really don't worry about memorizing it. It's just good to know it exists. There's ideas of swap gates and controlled swap gates. It's just an extra gate that's good to know about. Very importantly, notice that this has changed. So now we've just rewritten the state up here. This is what we have so far. Now what we do is we apply an H gate on the ancilla again. We just kind of, in some sense, try to undo it. Now this looks really complicated at first. If we expand this out as the plus state and this is the minus state, we get this whole complicated mess. But we can simplify this a bit into this state. What this leads to, this complicated state, what this leads to is that the probability of measuring 0 in the ancilla, that's the fundamental question that we're gonna ask here in order to get at the fidelity, is this. The probability of the ancilla being 0 after doing all of this complicated mess is 1/2 times this number here plus 1. Now, I encourage you to go back through this and derive this yourself using your math if you're curious, but I do want to emphasize you do not need to have done that yourself. You don't need to do that yourself. Just trust me, it does come out to be this. And a really nice way to write this is that the probability of the ancilla being 0 is just 1/2 times the fidelity plus 1. So we actually naturally get the fidelity encoded in the probability of measuring 0. And that's why we run this circuit, because we can rearrange this equation and say, if I run this circuit a bunch of times and I get a good estimate of the probability of measuring 0, well, all I do is plug it into this equation and that gives me the fidelity. So I can actually experimentally or in simulation run a circuit a bunch of times, measure the 0 or measure the ancilla for 0, and calculate the fidelity. I can get an experimental measure of fidelity. This is something that scientists really do in labs today. This is also something we're going to do now. Now, that was a lot of detail. I want to show it to you, but let's say that's looking a level deeper than we really need to go. So I just want to step back and summarize for a second. Fidelity is generally a way to measure how similar two states are, such as the same state with and without noise. And we can find the fidelity experimentally using the swap test. So let's code this now. And I will acknowledge for the folks in the group, you are more than welcome to take off. I know we're a bit over time at this point. You're more than welcome to go. And I just encourage you to watch the recording for the rest. But now I'm going to go ahead and work on the rest of the notebook with you all. This is the rest of the lab, is just working through this notebook and seeing this in action. So let's go ahead and try to characterize noise in circuits with the swap test. Specifically, we're going to see how to perform a swap test to calculate the fidelity and then use it specifically to characterize the noise present in a circuit. So the first problem, 2.1.1, let's see how to implement a swap test for this two states 0 and 1. And we're going to do this in our four-step process as we had before. First of all, we're going to prepare the two qubits in the given states that we want. We're going to append the swap test circuit. We're going to run it and calculate the fidelity. So first of all, we're going to prepare two qubits in the given states and one ancilla qubit in the 0 state. Specifically, we have this list, basically. Now we're going to have our qubits. We've gone ahead and named them just to try to keep track of what they are. We have state 0, state 1, ancilla. And what we do is in our circuit to prepare the 0 state, we create a separate circuit for each. We want to create the 0 state here for the 0 qubit. That is the equivalent of just doing nothing to qubit 0, or applying the identity gate. This just ensures that this has this here. You could get away with not using this. You could not have this line at all. I'm doing this just to make it very, very crystal clear that basically what we're doing to the 0 qubit on the 0 circuit is nothing. This is the circuit that specifically prepares qubit 0 in the 0 state. Now we want a circuit that prepares the qubit 1 in the 1 state, so we need to apply the X gate on that qubit. Then we want our final circuit that puts the ancilla into the 0 qubit, or into the 0 state, the ancilla qubit into the 0 state. So what we can do is we can say circuit 0 plus circuit 1. And if you wanted, you could do something, you could append to this something like circuit.append circ.I of ancilla. Again, that is completely optional. You don't have to do it, but it's there if you want it. So we go ahead and do this. What we're doing is we're preparing qubit 0 in the 0 state, qubit 1 in the 1 state, and then we're just putting them together. We could have defined this all as one circuit, but it's kind of nice to just keep them separate for a moment. Now we want to append the swap test circuit. So let's define the swap test circuit in our 4 steps here. First, we want to apply an H gate on the ancilla. So we put that here. We put the ancilla in superposition, so circ.H on ancilla. Then we want to controlled swap controlled by the ancilla and targeting Q0 and Q1. What that means is we start just like with a C0, we start with the control, so that's ancilla. And then we target Q0. Now where it gets a little different is we do Q1. So it's a little different because we're targeting multiple qubits. So unlike the C0 gate, we don't end just here. We just list the 2 ones we're going to swap. Q0 and Q1, we want to swap their states controlled by the ancilla. Oh, with a controlled gate in circ, you always start with the control qubit, and then you just list the targets after. Okay, then we want to apply an H gate to the ancilla again, sort of this symmetry here, H gate, C swap, H gate. And then we measure, and let's look at the result. So again, this may be very complicated. This is a really intense circuit, but this part actually is going to be the same every single time. So we get out this circuit, and now we can go ahead and run this. We want to run it 1,000 times, so I need to specify 1,000 repetitions, and let's look at the result. And of course, when we just print out the results, okay, that's not very helpful, but do notice we get a mix of zeros and ones, so we're going to be able to get some sort of probability out of this, probability of 0. So here we want to get the fidelity from this, which is to say that we use the measurements to calculate the fidelity by using this equation. The fidelity is 1 minus 2 times the probability of 0. So we do 1 minus 2 times the probability of 0, which we've already measured here. If you're curious, I encourage you to dig into this equation up here, but just know this is the probability of measuring 0. And we can get this, and we get out this fidelity here, this fidelity here. Okay. Now this is really, really low. Yeah, let's just run this. So yeah, this is really, really low. It's going to change a little bit each time, But generally, it's going to be really, really low because we have very different states here. Okay. Now, we can do the same thing here. Now, because we're over, I'm just going to go ahead and do this down here. Okay. Now, I will say one thing that I'm just taking a moment to pause on is the fact that we have the 0 and 1 state. They should actually have a fidelity of 0. They should be exactly 0 and opposite of each other. But instead, we just get this kind of low number, but it's not 0. And I just want to acknowledge that. What that is that this is a simulation. We ran this 1,000 times. We're working with 1,000 numbers. Technically, to know for a fact that it was 0, we'd have to measure this an infinite number of times. That's obviously not going to be realistic. We cannot do that. So we run a bunch of times, and the more times you run this, the more you should find that this dips down, this goes to 0. Okay. So it should be 0, and the more you run it, the closer it should get. But for now, we're just going to accept, okay, that's really, really low. It's like saying you have a 2% similarity in the states. 2% similarity. It's not very much. Okay, now we're going to do the exact same thing, but for the one state with itself. So here, circuit 0 is going to be actually applying the X gate to Q0 because we want that in the one state as we have here. Then we do the same thing to Q1. And then similarly, we go ahead and add these two circuits together. Then we're going to go ahead and create our circuit. Again, we have instructions here, but it's actually going to be the exact same thing as before. So I can just cheat and go ahead and copy and paste from above and run this. And now let me actually run the circuit. Let me simulate it, do it 1,000 times. And we get out this result. Notice we're getting a whole lot of zeros there. And then we have our equation 1 minus 2 times the probability of 0. And out comes 1. So in this case, we're actually really, really sure the simulation works really, really well. Generally, when the states are going to be the same, the simulation is able to find that pretty easily. It's not just the same, it's a classical state, just one. They're always identical. There's always going to be overlap. So switching them has no real effect because you're just switching one with itself. The moment you have a different state, switching it around can create some imprecisions in the simulation. But generally, notice when the states are the same, what we get out for this fidelity is really high. It's 1. And the farther apart they are and the more we run it, the lower that number gets. Now let's do it for kind of states in the middle, 1 in the plus state. So, okay, again, really going to encourage copy and paste. Let's copy from above, but instead of preparing the 1 in the 1 state, we want Q0 in the 1 state, so that's fine, but we want Q1 in the plus state. So we want to use an H there instead. That's our preparation. And then the rest is actually identical. It's just the preparation that's different, but the swap test is the same. Once you have it right once, you can just run this again. And let's simulate it and see what we get. Again, we have the equation there, 1 minus 2 times the probability of 0. And look, it's not quite 0.5, but it's very, very close. Roughly, they're 50% the same or so. That makes sense. We should get something around that. Right? We have the 1 state and the plus state. They are about 50% the same. They have 50% similarity. And so what we end up getting is something very, very close to this, right? And if we ran it again, because it's a simulation, we'd get a different result. And you can see this can vary a decent amount, but notice that it's not really that close to 0 and it's not really that close to 1. It's pretty much right in the middle. And you can imagine the more times we ran this, the more certain we'd get that it would be 0.5. So all of this is to show how we do this, but mostly, because you can copy and paste the code, mostly just to get the idea of what fidelity is. So now let's go ahead and just combine all of that into one cell so that we can make this a little easier to copy and paste in the future. So we want to prepare our qubits. It's literally the exact same problem. So we're just literally copying and pasting. Swap test circuit. Then we want to run the circuit. And we want to calculate the fidelity like we have here. Okay, so all I've done is literally copied and pasted the work from the problem above and put it in one cell. If you run it again, you should get the results. And here, beautifully, we can just rerun and rerun if we want. But this basically puts it all together. Now we can get to the final part, which is to actually use this to measure the effects of noise, as in how far does noise bring us from our ideal state. So here you can see we have this cell very similar to what we just created up here. It's already filled out for us mostly. There's just a couple points we need to change in order to specifically calculate the fidelity of Q0 in our typical ideal zero state, meaning ideal, meaning there's just no noise, and Q1 in a zero state prepared with a 5% chance of depolarization. So what we have here is the same exact circuit, but now what we want is for our full circuit to be Q0, and then we want Q1 to have a 5% chance of depolarization. So the only thing we need to adjust here from our code is that we create a noise model that's a 5% of depolarization, 5% chance, and that we then apply that here. This is the only part we need to change in the cell, which is we prepare our circuits, our qubits as normal, but then we say, qubit 1, that circuit's going to be able to have a little bit of noise in it, this 5% of depolarization. So now we can run this. All the rest of the code's provided, and it's the same as we developed above. And look at this, 0.966. Even though we ran this exact same circuit above, where basically it was the equivalent of this with 0, and we got out a nice 1, right? We ran this 1,000 times, and in every single case they agreed. The moment we had even just 5% noise in here on qubit 1, suddenly they don't agree with each other. And the exact amount is going to change each time because it's a simulation. It's not perfect. It's not all of reality. It's just little data points. But notice we start to lose some confidence. We lose some fidelity in the results. Okay. Now let's do the same thing, but where there's a 50% chance of depolarization. So it's the same thing here, depolarization, but instead of 0.05, it's 0.5. So it's a ton more likely, 10 times more likely that we have noise. Let's go ahead and run. And they should be the same. We should have 100% fidelity, and yet we're getting out about 67%. About 67% of this time, they agree with each other. So clearly, just adding this noise on just this qubit to prepare it is not great. And what we've done is we've said, okay, if we had a circuit where we tried to prepare the one state with 50% chance of depolarization, well, roughly 67% of the time, I mean, that's not exactly fidelity, but we would have a 67% fidelity with the ideal state. It's not very close, 67% overlap with it, not very close. So now we're going to go ahead and build on this even more. We're just building up layer by layer. So I know it's getting very complex, but we're going to get a really nice visual out of this in the end over the next few problems. In particular, we're now going to use a loop. So, okay, if you're not that comfortable with loops, I haven't used them too much, but we've seen them. Use a loop to run the experiments from above, but for many depolarizations, particularly ones given here. So this whole range of them, we just have 20 different values basically between 0 and 1. And now we want to run this. Now, the only part we need to actually complete here, you don't have to worry too much about the coding. The only part we really need to complete is specifying the exact noise models used in each iteration. So all of this is provided for us. It's all the same as above almost, except here we need to create the noise model. So our noise model is circ dot. We want depolarizing noise. And now we want to specify the probability. But here we're actually looping through the different probabilities we're looking at, each of the ones in this list. So this variable here, prob, represents that. And basically what we're doing is we're running through the exact same circuit we had above, but for a range of probabilities. And each time we add the fidelity we get to a list, and then we can go ahead and look at the results. Now we're running this a lot of times, a lot of different ways, with a lot of different probabilities. So this is going to take a little bit to run. While this is running, if any folks have any questions, let me know. If you're also looking to go through this more quickly, just as a recommendation, you can decrease the number of repetitions. Your results will be slightly less precise. You won't be quite as sure of them, but honestly, it'll be pretty easy to do 100 and still get decent results. It'll go much faster, 10 times faster. And here we get a list of fidelities. So when we have 0% noise, okay, we have an 100% fidelity. You're 100% certain they're going to be the same states, but then notice that these start to drop. Now, because looking at just a list of numbers can be very confusing on top of all of this, it's very nice to visualize it. So we've actually provided code here that you can just go ahead and run after you've run that cell. And it shows you not only the results you got from your simulation, but it also shows you the actual theoretical results. Now, this is well beyond the scope of this course, but it is something that if you study quantum computing in college or beyond, you will see this. It's not that far off to study this. And you can actually come up with an equation that specifically defines what fidelity you would expect. And here we get the theory is shown as the straight clean line in orange, and the simulation results in blue down here. You can see they're not exactly the same. They're actually a little lower each time. But basically, this is what happens. We get very close to the theory, and generally you can see it's kind of like a straight line going down or sloping down more and more, but generally it sits right along here. Generally, as your depolarization probability goes up, the fidelity goes down. If you take away anything from this plot, it should be that. As you get more chance of depolarization, the fidelity of the ideal state and the noisy one goes down. Okay, now we're going to do this in an even more realistic way, and I will say this is the very last exercise. I know we're running over quite a bit, and this is very advanced stuff, but I just want to make sure you have this for your own curiosity. So we're going to run this in a more realistic way where we have noise in the whole circuit. As in, any of the qubits, including the ancilla or qubit 0, could have noise on it. We don't know when it's going to strike. We don't know if it's going to strike, how many times it'll strike, who it'll strike. It could be anywhere. So now we have the exact same code as above. But instead of specifying here in our circuit, hey, circuit 1 has noise in it, we're actually going to go ahead and specify that we're just going to simulate the whole resulting circuit with the swap test and everything with noise in it. So first we have to create our noise model with the given probability in that loop. And then we want to simulate that circuit with that amount of noise. Now, one thing to note here is I'm going to make the repetitions, and this is in the note in the text. I'm going to make it 100 instead of 1,000. As I said, this actually makes it 10 times faster because instead of doing 1,000 every time, we just do it 100 each time. If you're willing to wait a little longer, you can make this more and get more precise results. It should be closer to the theory, in other words. But this will be a little faster. So for our sakes, we're just going to run it and it'll be good enough. It should still be relatively close. It still will take a little bit of time to run. But basically, we're doing the exact same thing as above. We're running over depolarizing noise for the same probabilities of noise, but we're looking at it throughout the whole circuit. And now we can see not only the theoretical results and our simulated results from above, but we can see an orange here now. So we have green for the theory at the top, blue for the simulation from earlier, where it's specifically just been preparing one state. And then down here, we have this mess that represents the full noise simulation that we just ran. And you see it's much lower. There's a much lower fidelity. And then it still also decreases, but it very quickly basically just gets very, very low, where you have a very unlikely chance of getting the right state out. That's because now we're not even sure what we're measuring, because what we're comparing to is not reliable. So it's not just we're saying we have a noisy and an ideal qubit that we're comparing to. We're comparing two noisy qubits to each other. What states do they end up with? Well, they could both flip. They could both be the same. They could both get changed in a million different ways that could be the same or different. And your swap circuit could even be incorrect, like we saw in preparing the Bell state above, where you have that noise matters. Here, maybe you get it at a point that matters and your swap test just gets destroyed. So what we're even measuring isn't really even the fidelity. So this is to show really the most realistic situation, unfortunately, which is you have noise everywhere, even in the circuit that you're trying to build to measure the fidelity. What this shows is, if we want to at least get a sense of this in practice, of the fidelity in practice, maybe it'd be worth building some device that's really, really good at running the swap test, like some swap test circuit that's built in, that's super low noise, really good at doing its job, so we can rely on it and at least get results closer to these blue dots that we simulated versus this. But if we get results out and they look closer to this, then we also still have an idea of what's happening, right? We have these simulated points and theoretical points to compare to. So now the next step that an engineer would do is go out and run this on a real quantum computer, this exact same circuit that we've defined here. And they would say, which of these is it closest to? Is it the theory? Is it the simulation where there's a bit of noise on one qubit? Is it the simulation where there's noise everywhere? Or is it somewhere in between, which is probably what you'd see? And it can tell you how close you are and what situation's happening. On the other hand, if you get a completely different shape from all of this, some wild other shape that's not any of these lines, not this, it doesn't even look like this, maybe it crosses up or something like that, well, then you have a different type of noise or something else going on. And that's a sign that you'd need to investigate other noise models. So this is what we do in practice. We run these simulations, we run these swap tests in simulation and on the hardware, and we develop theoretical models, and we try to just compare them all and basically just match them up so we can really understand what we're looking at in practice in terms of what noise models we're seeing, how close we are to the theory, where the noise seems to be, all of this. So this really is something that scientists would do in practice. This is a set of simulations that researchers really do, that you've just done. And for homework, you're actually going to see this in practice with a different type of noise and see that these shapes actually look very different. So you're going to develop this exact same thing, but with a different shape. Now, I do want to point out before we wrap up here that we have provided a noisy simulations cheat sheet. And this has everything you need in terms of defining all sorts of different noise models. It also has the full code for everything you need for these characterizations. So I know this is a lot of code, but I highly recommend you just go in here and this will just make your life a lot easier. You can just use this. And really what I want you to focus on is just changing the parts of this that you need to for the specific homework prompts. Okay, so this is more about modifying this code than coming up with it from scratch. Okay. So generally, we saw how to create noise models, how to create a swap test, and how to use it to measure some noisy states. This was a lot of stuff, but with that, I'm going to go ahead and wrap up, call it a day. I hope the two of you that stayed on for all this time enjoyed. I'll do have to get going. I hope you have a lovely day, lovely week. And if you have questions on this, look at the cheat sheet, go to office hours, and otherwise have a lovely week. And next week, we'll be back with what we can do about this noise, specifically in the form of error correction.